Hello everyone, welcome to our session. Today we are going to discuss about trigonometric substitution. So those integrals that involve square roots, such as this square root of a squared minus x squared, or if our integrals contains this square root of a squared plus x squared, or can be square root of x squared minus a squared, then we are going to use the trigonometric substitution, where from this square roots, a here and also the a here and also this a is a constant, and this can be solved using trigonometric substitutions. So these substitutions are as follows. I don't want you to memorize this. In our next video, I will teach you how and why we need to derive this. Okay, so these substitutions are as follows. We need to use x equal to a sine theta for integrals with this square root of a squared minus x squared, and x is equal to a tangent theta for the integrals with this square root of a squared plus x squared. And we can use this x equal to a secant theta for the integrals with this square root of x squared minus a squared. Okay? Now we have here reference triangles for trigonometric substitution. So the first one, we have here the right triangle. This is the legs of this right triangle, and we have here the hypotenuse. So one of the legs is labeled as x and the hypotenuse as a. And notice here that this side here is color blue. So in our next slide that contains also reference triangles, just observe the side with the color blue. So this is the side that we're going to solve using Pythagorean theorem. Alright, so by Pythagorean theorem we can solve this because Pythagorean theorem says that the square of the hypotenuse is equal to the sum of the squares of the two legs, right? So from that theorem, we can solve for this side. Okay, so to solve this side, if this is the hypotenuse, okay, this is the x, you square that one, you square this one also, you sum up, and then we have the square of the hypotenuse. But since this is the side that we're going to solve, then therefore we have the square of this one minus this, the square of this, then take the square root, so that would be the length of this leg or side of this right triangle. Then from here we can solve our x by using sine trigonometric function, sine function. So why we choose sine? Because it's easier, because when we use sine, we can avoid this part that contains the square root. So when we speak of sine, so that is opposite, right? Opposite over hypotenuse. Sine of this angle, from definition, it is opposite side divided by the hypotenuse side. Then to solve for x, we just cross multiply a, then we will get x equal to a sine theta. Now to solve this, we can use cosine. So from our definition, cosine is adjacent. So this side, cosine of this angle theta, adjacent over hypotenuse. So therefore we can solve this by just cross multiplying a, cross multiply and multiply to cosine theta. So therefore we have this side equal to the square root of a squared minus x squared, which is equal to a times cosine theta. Next, we have this reference triangle. So notice here that the hypotenuse is now colored blue. So this is the side that we're going to solve. So from our definition of Pythagorean theorem, so this side, the square of this side is just the sum of the squares of these two legs. Okay, or we can say that this is just the square root, no? This side here, square root of the sum of the squares of these two legs. Now we can use tangent to solve for x. It's much easier to use tangent because we can avoid this part here that contains the radical or the square root. So when you take a tangent of this angle theta is equal to opposite divided by adjacent. Okay, then solving for x, you have x equal to a tangent theta. Now to solve this, we can use secant. So from our definition, secant is hypotenuse over adjacent. This one, then cross multiplying a, then we can get this side, which is the hypotenuse, equal to a times secant theta. Okay, then the third one, so as you have noticed here, this is the side that is colored blue, and these are the sides that were labeled as x for the hypotenuse, a for the this side, for one of the legs. Okay, then by Pythagorean theorem, once again, we can get this side. So that side would be the square root of the square of this hypotenuse minus the square of this leg, this side here. So that is the length of this side. Now for our substitution, it's much easier for us to use secant, because when we use secant, we just involve this two sides. We have this leg and this hypotenuse. So from our definition of secant is hypotenuse. Okay, secant theta is hypotenuse over adjacent. Okay, cross multiplying a, then we can solve x equal to a secant theta. Then for this side, to solve for this side, it's easier for us to use tangent because it involves this side and also this side here. So tangent of this angle theta is just opposite over adjacent. Cross multiplying a, then we will get this side, which is equal to a times the tangent theta. Alright, so that's it for the introductory part of this topic, trigonometric substitution. I'll give you details of how these equations were derived in our next video. So we have here some sample exercises that we can practice, and we will have another video for the solution of this problem. Okay, thank you very much. Bye. See you in our next video.